Okay, looks like I'm a minute late here. Sorry about that. I was just getting things loaded up. And one thing I wanted to start out by saying is I'm sorry. The judge program on the AutoGrader that tells you whether your project is right or not, I don't normally mess with it while a project is live. And I did so this time because I've been trying to make the judge better to give you more meaningful feedback when your test case fails, that you'd get a little bit better feedback to help you see more about what is wrong instead of just getting a few characters. And I made a mistake in it that then was giving basically if you had the word that the morph mode should have produced, you got it marked as right. So I'm sorry I had to tell everyone to make sure you resubmit after that. I don't usually, like I said, make changes like that while the project is live, but I've been trying to improve this one and the AutoGrader, the judge that goes with the project, to make it a little bit better. Okay, so today we're going to talk about recursion. And just a little bit of review here. Remember, recursion is a function that calls itself to complete some task. And then when we do that, we've got to have at least one base case in the recursive function so that it can have a stopping point. We've got to have at least one recursive case so that we have a path to follow when we need to solve the large problem. When we make each subsequent call to this recursive function, it's going to have a simpler or smaller input. We've got to somehow make progress towards the base case. And then so something like a single recursion, a function that has within one call, it calls itself at most once, can be used on things like lists, like binary search. And when we say lists, we mean basically a linear data structure, not necessarily a linked list. But we could use single recursion on something like a vector. When we have a tree, we would use multiple recursion, where we might say, hey, let's print out what's in this node, and then we'll make a recursive call to the left, and then we'll make a recursive call to the right. So when we do trees and using recursive algorithms, we'll often have multiple recursive calls. And there's other cases where we might have multiple recursive calls. Now, remember we talked about this problem of having a power function and writing it out, having a linear solution and having a log solution. We worked on that last time. Now, when we look at writing out the problem, there's two different problems mapped out on this page. So the first problem is is doing the exponential, sorry. It's the same problem solved two different ways. The first one is solving the exponent by doing a multiplication with a recursive call that's a size 1 smaller. And then the logarithmic solution solves it by splitting it into a call, really. We make this recursive call and we multiply it by itself. We don't necessarily call it twice. I'm going to call it once and remember that result and then multiply it by itself. And we would call it once whether it's even or odd. The difference is when it's even, we just make the recursive call, multiply by itself. When n is odd, we make the recursive call, multiply by itself, and multiply by x. And notice we showed in here specifically the floor of n over 2. Now really, when we do code, most programming languages that deal with integers do integer division. So like C++, C, Java does integer division. So there's our two solutions. We've got our O of n solution. We've got our O of log n solution. And we worked last time at solving the equations for this. Okay, and we've got the recurrence relations there and the complexity. And we did the solving of those last time. It's odd that nobody has said anything in chat. It says we've got hundreds of concurrent viewers and nobody's typing in chat, so hopefully it's working. At least for me, live chat seems to not exist. I'm afraid to refresh the page because my stream might die if I do that. So I cannot see the chat. Hopefully the staff member or another faculty is dealing with that. And I don't want to open up normal YouTube because then I'll get an audio feedback loop. Let me see. Okay, my audio, I'm just double checking. My audio is working. So I would hopefully, normally I could see the chat. It's just it didn't display properly this time. I'll have to start the YouTube website a little bit earlier next time to make sure that's working before I start the streaming. Okay, so talking about tail recursion. So when a function calls itself, or really not even calls itself, when a function is called, a stack frame gets generated. And the stack frame stores local variables and other things. We'll look at a more detailed view in a minute. Now, when we have a recursive function, it generates a stack frame for every recursive call. And then if a function is tail recursive, if there's no operation pending after the recursive call finishes, the compiler generates code to reuse the stack frames. And that makes it more efficient. It makes it faster, and it makes it safer because the stack size is limited and we don't want to run out of stack size. And so if we have a non-tail recursive function, we have to worry, what if someone called this with input that's so big that I run out of stack space? But with tail recursion, we don't have to worry about that because we keep reusing the same stack frame over and over. And it says at the bottom here, tail recursion and iteration are equivalent. What that means is that if there is a tail recursive solution, you can write an iterative solution. And if there is an iterative solution, you can write a tail recursive solution. When that is the case, that it can be done either way, I would say write it the way that's most comfortable to you. And that changes with your experience, and it changes with the problem. Some problems will be easier, will be more obvious as recursion, and others will be more obvious as iteration. Even as you get more confident and more exposed to recursion, you'll become more comfortable with it in general. But even being really good at recursion, some problems I see the iterative solution first. Now, when we talk about recursion and the stack, we've got an example here of main calls factorial of 5. Now, we really should have just a little bit more in main here, like maybe a cout less than that, less than EMDL. Okay, so we're actually going to display it once it's done. We're not just going to call it and have nothing happen with the result. Okay, so if we do that, what happens is the stack inside of the computer, we get main. Main gets put on the stack. There might be stuff below main that's sort of like the code that the compiler generated, but main is the first thing that is identifiably ours that we wrote. So we've got main, and then main starts doing a cout. Well, cout says cout can't be called until both operands are ready, because think of this: cout is an object. We're doing cout dot operator less than of whatever. So cout less than factorial of 5 is the same as writing cout call your operator less than on the result of factorial of 5. So until this factorial of 5 is done being computed, the cout less than doesn't even start. So main starts running, and then factorial starts running, because that's got to be done before we can send it to cout. So factorial, and I'm just going to write fact here. Fact of 5 goes onto the stack. Now let's look at our code here. This one says return n times the recursive call. Well, because there's a pending operation, there's a multiply that's pending when the recursive call finishes. We make a recursive call and we can't reuse the stack frame. So factorial of 4 goes on the stack, and factorial of 3 goes on the stack, factorial of 2 goes on the stack, factorial of 1 goes on the stack, and then let's look at the base case here. It says if n equals 0. So I'm running out of room there. Factorial of 0 goes on the stack. Factorial of 0 is a base case. It immediately returns 1. So there's this one's ending, and somehow we got to get a 1 back to there. And then factorial of 1 returns 1 times the recursive call. So a 1 went there, then this one ends, and 1 goes back here. This one ends, 2 goes back there. This one ends, and 6 returns here. This one ends, 24 goes back to there. This one ends, and 120 goes back to main. So all of the factorial calls happened, and then they all unrolled one after another with things getting popped off the stack and things returned. So let's look at a more detailed view of what's going on behind the scenes here. So when a function call is made, all local variables are saved in the stack. Now, what does it mean by local variables? Well, you'd say, well, aren't those in their own place in memory? Where they are generally is inside of the CPU. So the CPU has a bunch of locations in it called registers. And everything has to be in the CPU before your code can do anything with it. So what happens is the local variables, the code that's generated by the compiler, when you've got a local variable like n, the compiler says, ooh, let's put n in a certain register. Now, if we make a recursive call without saving the contents of those registers, that function we call might change the value of those registers. So we've got to save them. So when we say we save the local variables, what we're really saying is we're saving the registers. We're saving a copy of the CPU registers, so then that new function can use whatever registers it needs to. And the compiler tends to generate very consistent code. It's like, oh, I'll put parameters will go in these registers and local variables will go in those registers, and that way when the function gets called, it knows where to look for its parameters because the same compiler generated all of the code. Okay, so we save those local variables, those registers, into the stack. Then any arguments that are going to be given to the called function go into the stack. So I misstated that. It's actually dependent on architecture. Some architectures will pass, like if a function has 1 or 2 arguments, we might just stick them in a register. If it's got more arguments, we might have to put multiple ones on the stack. So it really depends on the number of parameters, the exact compiler and the architecture, and how they decide to do things. So we might pass some parameters on the stack, or in registers, but there's a fixed number of registers. There's a small number of registers. So if your function has 12 parameters, well, no, there's not going to be a register for every one of them. So parameters get pushed onto the stack, the arguments get pushed onto the stack, and then when the function call is received, those function arguments go into local variables, into what are registers. So even if they were on the stack to begin with, every time we want to do something with them, we've got to get them off the stack and into a register so that we can do operations on it. Then when this function issues the return, it's got to put the return value on the stack, and then it's got to go back to where it came from. How does it know where to go back to where it came from? How does it know who called it? Actually, that's another thing we sort of glossed over here is the return address. is one of those things that has to go on the stack. So before this function returns, it gets off of the stack the address. Where am I going to return to when I return? So then when the return is received, so back in the calling function, or it says the call site, the function that did the calling, when that one gets back to itself, it says, hey, my call to a function is over, therefore I'm back in my code, and I'm going to go and get that return value off of the stack, put it into a register so I can do something with it. And it's going to get the local variables, all those CPU registers, go back, get restored from the stack. So when we have a program that has 6 nested calls, like main calls function A calls B calls C, if there's 6 nested calls, there's going to be 6 sets of local variables on the stack. There is only one program stack. Now I put in parentheses there per thread because although we don't do multi-threaded programming in 281, I hate to give you half of an explanation. So if you're doing multi-threaded programming, then the operating system and your program in memory has to keep track of one stack for every thread that's currently executing. So that's more storage. But we can take the view that there is one stack because we're only doing single-threaded programming in here. Now this is not the same place as the heap. It all goes into memory, into your RAM chips, but this is separate from the heap where new is done. So this program stack size is limited, and it's limited by a combination of the compiler, the operating system, the hardware that you're running on, how much memory exists in it, etc. And so when your program starts, it knows how big the stack can become. And if we run out of stack space, then we might be unable to make another call. And if that happens, we get what's called a stack overflow. So that's what happens when we have, say, a function that's not tail recursive, and the number of calls, the number of recursive calls gets large. If n is large enough, we might overload the stack and we get a stack overflow. And this situation is kind of common. There's a whole website based on the name now, a programming website. So when we have straightforward recursion, we have O of n time, or big theta, we said, big theta of n in time and big theta of n in space, and that space is the stack frames, that n stack frames. And yes, there's n of them, and there's a constant amount of information in each stack frame. There's whatever local variables have to be saved, there's whatever parameters we're passing, which is one integer, and the return address. So that's a fixed amount of information, but there's n copies of it. Now, if we change to a tail recursive version using the default parameter, then because it is tail recursive, because there is no operation pending, whoops, got a little bit out of line there. Because there's no operation pending when the recursive call ends, because we can immediately return after the recursive call ends, we don't need those stack frames. So when we say we reuse the stack frames, what does that mean from 2 slides ago? What it means is I don't have to do step 1a. I don't have to do step 1a because I don't need my local variables. When that recursive call is done, I am done. So I don't need to do step 1a if I'm tail recursive. Step 2a, the argument values are pushed on the stack. Well, what we do is we don't push them onto the stack, we reuse them on the stack. Because like in this function, let's go over here, in this function, I've got 2 parameters, n and result. When the recursive call is done, I don't need n any longer. So the n that I want to give to the function I'm calling can replace my copy of n on the stack. The one that I was given gets overwritten with the one I want to give to someone else. And whatever my result was when I came in, or actually whatever it is right now, it gets replaced with what I want to pass to the function I'm calling. Because I don't need them anymore. Once the called function is done, I'm done. And we do not, when we're in a recursive call, we don't push the return address onto the stack. We leave it alone because the return address on the stack is the one back in main that started the recursive calls. So when main calls factorial, main says, return to me in main at this memory address. But then when factorial calls itself, it leaves that address alone and says, hey, when I'm all done, I make 6 recursive calls. When the base case is done, the base case returns straight back to main. It does not go through each of those pieces of the stack. It goes straight back to main, and then main gets rid of the one copy of everything that was on the stack. Okay, so we did the power last time. We can use the default parameters to make a logarithmic version of power that is tail recursive. So we always call it with x and n. Notice we do the multiplication first. We multiply x times x, and then we say take that to the n over 2 power. So if I was trying to do like 2 to the 5th power, all right, I'd say, well, I'm trying to do 2 to the 5th power. Is n 0? No. Is n even? No. So what I have to do is I've got to multiply x times x. So I'm going to do 4 to the n over 2. So 5 over 2 is 2. I need 4 to the 2nd power. And my intermediate result is my existing result, which is 1, times x, which is 2. So that's what it says. It says calculate 4 squared and then multiply it by the result. That is 2, which gives us 4 squared is 16. We end up multiplying by result at some point, and that's our 2, and we get 32. So 4 squared is 16 times 2 in the recursive calls is 32. We're going to return 32 back to main. So how do we get there? So we're in the recursive call now. We're trying to calculate 4 squared with an intermediate result of 2. Okay, it says, so we go back here, we say, is n equal to 0? No. Is n even? Yes, n is even. So I want to return 4 times 4 is 16. So I've got to return, so I've got to make a call with 16 to the 1st power, and my intermediate result is 2. Okay, so that's what I need to do right now. I need 16 to the 1st power, and my intermediate result is 2. We need to change colors again. Okay, so now I'm trying to calculate 16 to the 1st power. I say, is n equal to 0? No. Is n even? No. Okay, so n is odd. So I need to calculate 16 times 16. Wait a minute. I don't really need this, but it's the way the recursive call works out. So it says, I need to make a recursive call of 256 to the 0th power, and my intermediate result is 16 times 2 is 32. Okay, so now I need another color. So now we get to a call. We're calling 256 to the 0 power. We say, is n equal to 0? Yes, it is. We're at a base case. Return result. We don't even look at that x. X is nonsense at this point. We've got the result. We return 32 all the way back to the original calling function. It goes straight back to main. Main gets 32. All right. So I know this one may be a little bit confusing. If you have to, go back and re-watch this later. Type the code into your favorite IDE and run it and watch it run. Okay, so practical considerations. So we said before the stack size is limited. So it's actually pretty easy to exhaust that. And the more parameters you have, the easier it is to get to exhaust it. So the more parameters you have, the more local variables you have, the faster the stack space will run out. So with, like, say, one integer, you might be able to make like 5,000 or 10,000 recursive calls. But if you have like 4 times as much parameters and local variables, it might exhaust that memory 4 times faster. So instead of 10,000, we might be down to 2,500 with more parameters and more local variables. And so for large data where we don't know how big n is really going to be, simple recursion is a bad idea. I had someone ask me yesterday in office hours, should we be using recursion in Project 1? No, because we don't know how big n is going to be. And actually, this is a good point to mention something about Project 1. So the project spec says you can't make any assumptions about how big the dictionary would be. We can make a little bit of assumptions. We can assume that the size of the dictionary is less than 2 billion. And what that means is that we can use things like int or int 32 underscore t, or better yet, uint 32 underscore t. So all of those allow integers so integers have a range of -2 billion to +2 billion. An unsigned integer has a range of 0 to 4 billion. So with that, we can fit our dictionary in there. But you aren't allowed to assume, hey, the dictionary, I've never seen one with more than 20 words. No, we do have a dictionary with on the order of 400,000 words in it. So the recursion in Project 1 is the wrong way to go. That's why we gave you the algorithm, told you to use on the command line a stack or a queue, or better yet, a deck. But when we say use a stack, you can't do recursion and use the call stack because you'd go over the stack space with 400,000 words. Okay, so if we have large data, simple recursion is a bad idea. We could use tail recursion or an iterative algorithm, and that's what we're doing in Project 1. We're doing an iterative algorithm, and we're using a data structure to keep track of what's in the stack or queue. And you say, well, wait a minute. Aren't we limited in that too? We are, but the size of a stack, data structure, or a queue, or better yet, a deck, the deck size is limited by the heap, and the heap is bigger than the stack. The stack has a much smaller limit than the heap does. So in the heap, we might be able to fit like 2 gigabytes into the heap, but the stack will exhaust it with, some number of thousands of calls deep. But we can't reach 400,000 calls deep with a bunch of parameters. So it doesn't mean, however, this doesn't mean that everything you write should be tail recursive. So some problems just can't be done tail recursively. Like if we want to do a tree traversal, like if we want to do a print what's recursive, so make a recursive call left, print what's in this node, make a recursive call right, we can't do tail recursion there. We've got more than one recursive call. Now, as long as our binary tree is not a big stick, we'll be okay. And so we're going to learn later on in the semester how to make binary trees that have a guarantee on their height will not be O of n. We will be able to guarantee a binary tree with a height of log n. No matter what order you insert things or delete things or whatever, we're going to put a guarantee on the height of that tree. So we aren't there yet, but when we get there, we'll be able to do things safely with binary trees. Now, here we've got a set of different recurrence relations, and they can be used for different purposes. I could write a recurrence relationship for x, which we did today and last time. We could write a recurrence relationship for the time, and we could also write a recurrence relationship for memory. Usually the memory is easier to see than to see without writing a recurrence relationship than time sometimes is. So usually we're not going to need a recurrence relationship to see the amount of memory required. Usually we'll be able to see that, hey, we're making calls. And wait a minute, I solved the time was log n, and if my time is log n, then I can't have O of n memory on the stack at least. I might have O of n memory in the function, but I'm not going to have O of n stack calls. So if you solve the time, solving for time will sometimes give you a handle on the upper limit for the memory. Okay, so when we do a logarithmic recurrence relationship, and we solved this last time, we wrote down this recurrence relation last time, and we solved it out. Now this recurrence relationship works for different things. So for example, we had one last time. We were just looking at the recurrence relationship for our power, our logarithmic power function. So we used this equation to solve it. We got a big theta of log n. And this recurrence relationship is when I've got two halves and I've got one recursive call, and then we've got some constant amount of work done that's not recursive. This same recurrence relationship happens to fit binary search. So the search space is cut in half, that's our divided by 2, and we only recurse into 1/2, and besides the recursive part, there's a constant amount of work involved in those recursive calls. Things like calculating where the middle is, seeing if the middle is equal to what we're looking for, is that C1. Now we've got a table here of some common recurrence relationships and an example of an algorithm that uses that recurrence relationship and our solution. And we gave the big O here because if we had said worst case, we could have said big theta. Like for linear search or even binary search, they are O of n or O of log n. But in the best case, they could always be O of 1. We could get lucky. Remember, we can't change n, but we could get lucky and find it the first place we look, like in the middle for binary search. There's the one I was looking for. Or at the very beginning of the linear search, it's in the first place I looked. So we said big O here because this is the upper limit on how bad it could be. This is a tight upper limit. It is not, we're not just saying, hey, like n to the nth power just to be lazy. So this is a tight upper bound, but it is an upper bound. It's not a big theta bound because best cases could be better than this for some of these. Okay, so for binary search, we just had that on the previous slide. It gives us log n. The linear search, we say, hey, if you find it here, good. If not, repeat the search with n-1 elements. So if we solve that out, we solve that one with the substitution method, like 2 lectures ago, I think, and that one gives us O of n. If we had a tree traversal, this is like the binary search in that we've got to divide by 2, but in binary search, if what we're looking for is smaller than the value at the middle, we only have to look in the first half. Here we have to do a tree traversal, we have to recurse into both halves. I have to say, make a recursive call to the left, print the current element, make a recursive call to the right. Now, if we were to solve this, we would get O of n. Now that makes sense. If I'm trying to print all of the things in a binary tree, I have to print n things. That makes sense. So we could solve that one, but we want to get to the point where we don't have to solve all of these. So the next one there, it would be like selection sort, bubble sort, etc. T of n-1 plus C1 times n. So I've got to do some amount of work, some linear amount of work, make a recursive call on the unsorted portion, and some constant C1, C2 there. Merge sort and quick sort, which I believe you talked about merge sort in 280. So merge sort, we've got to recurse into both halves. So this part is similar to a tree search, but instead of a constant amount of work outside of the recursion, we've got a linear amount of work outside the recursion. And if we solve that one, we get n log n. Now what we want is we want an easier way to solve the ones that do the division. We don't have an easier way to solve the ones that do the subtraction. Those we got to go do the substitution method and solve it. But for the ones that divide, we're going to find a better way to do it. So like I said, we can do the substitution method, look for a pattern and get our formula. We can use the master theorem, which we're going to talk about in just a few minutes. And we can also use the recursion tree method, which is illustrated in CLRS. Now, I'm going to tell you one thing at this point. The master theorem is in CLRS, but don't look at it. Oh. The very first semester I was at U of M and I taught 281, I inherited slides from someone else. And I looked at these slides and I went, oh yeah, I remember how to do that master theorem from when I was a grad student and we used CLRS, yeah, no problem. And I was explaining it and I got done and I look at, I was in 220 Chrysler Auditorium. And I look around at Chrysler Auditorium and the students were like, just like stunned. And I said, okay, that was a bad idea. That is not the best way to explain it. So I came back the next lecture. I said, hey, I've got a new set of slides called Master Theorem Revisited. And just forget everything we did Tuesday. Here it's Thursday, and we're going to show you a better way to do the master theorem. And then the next semester, that became the only way we teach it. So if you look at CLRS, CLRS is an equivalent power. It solves the same problems, but it solves it in a different way. And the way that CLRS demonstrates it is harder to understand, and it's harder to apply to a given problem. So we're going to show you a method that is equivalent power, but much easier to use in practice, and much easier to see what is happening. Okay, so here's an exercise. So the idea is we're not going to solve all of these, but so if a recurrence cuts a problem into two halves and we have to recursively go into both, well, that's a recurrence. It involves division. What if it cuts it into three problems? Cuts a problem into three subproblems and it processes one of those pieces. What if it processes two of those pieces? What if it processes all of them? What if the non-recursive work was not constant? What if it was a linear amount of work? So, or an n squared amount of work outside of the recursive call. So there's all kinds of things that can happen here. When we cut it into multiple subproblems, and I'm saying dividing by a certain amount, not when we subtract one, but when we divide, there's a better way to do this. So let's look at what the master theorem says. So first of all, T of n. So T of n is our recurrence relationship. It says we're going to assume it's a monotonically increasing function, which means our time function always, as n becomes larger, T of n always increases. It never flattens out. It never ever goes down. So we've got to make that assumption for the master theorem to work. Now with computer stuff, this is a reasonable assumption. As someone pointed out, I think it was last time, when we said, hey, let's use cosine and sine for a counterexample, or one of the students said, let's use tangent for a counterexample. Great counterexamples, but in computer science complexity, they generally don't occur. So this restriction on the master theorem is not very restrictive. I've never seen an algorithm that had a sine time complexity. So our time function has to be always increasing. Monotonically means as n increases, t increases. It never goes flat, it never goes down. Okay, and it has to satisfy a few things here. So what we say it has to satisfy is, first of all, t of n has to be of the form a times t of n divided by b plus f of n. Now there's some restrictions here. So the second part here says we've got to have a base case. And it doesn't matter if the base case is when we get to n equals 1 or the base case is when we get to n equals 0. There just has to be a base case of either size 1 or size 0 is a base case, and the base case has to have a constant amount of work involved. So that's not too limiting. So it doesn't matter if our base case is size 1 or a base case is size 2, as long as it's a constant amount of work, we've got a good base case. Last thing, last restrictions here. It says where a is greater than or equal to 1. So we can't say like 0.5 times t of n. It's got to be 1 times t of n or 2. It could be a 0.5, but that would be really rare. And then it's n divided by b. It says b has to be greater than 1. Again, a fraction here would be odd, like 1.5. b being 1.5 would be kind of odd, but it's allowed. It just has to be greater than 1, what we divide by. So things not integers here are rare, but they're allowed to happen. Okay, and then it says, also, f of n has to be of the form big theta of n to the c. So what this is saying is that f of n has to be a polynomial. So f of n has to be a polynomial function. So if all those things are true, if it fits this form, a is greater than or equal to 1, b is greater than 1, f of n is a polynomial, then we've got 3 cases. So we've got 3 cases. It says if what we do is we figure out what is our a, what is our b, and what is our c. So it's a little bit confusing here because we use C0 and C1 sometimes. So a is right here, b is right here, and c is right there. That's the a, b, and c we talk about when we say, how is a related to b to the c power? We're talking about the exponent of the polynomial of f of n. So we say, how is a related to b to the c power? If a is greater than, we get the first form. If a is equal to, we get the middle form. If a is less than b to the c, we get the third form. And we're going to come back, after we go through these and some examples, we're going to come back and talk about what it means when a is greater than b to the c, or a is equal. Okay, so there's our rules. And what we want to do here is do a few exercises, and I've got everything we need written out. So here's our t of n, and I wrote almost everything. I didn't write the base case. Let's assume there's a base case. Okay, so assuming there's a base case, I've given you everything you need here. So we've got t of n. What I want you to do is just take a minute, figure out what's a, b, and c in that equation, and figure out which condition it is. And if you figure out which condition it is, what is the form of our big theta? Okay, so go ahead and take a minute to do that. I'm going to try to refresh my browser and see if I get the chat window back. Okay, well, for some reason my YouTube presenters page doesn't like me today. It doesn't want to show my chat window. So I've got it loaded up in a different window and got the volume muted so we don't get a feedback loop, just so I can see that, hey, people are participating. Excellent. Okay, so we want to get our a, b, and c out of here. So a is out front here. That's a is equal to 3. B is down there. B is equal to 2. And c is then, this is f of n. So f of n is equal to 3/4 n plus 1. That means, so we want to know f of n is an element of big theta of n to the c power. Aha! C is equal to 1. So we've got a polynomial. We've got a first order polynomial. So we've got 3, 2, 1. So now we got to check. How is A related to b to the c power? Okay, so how is 3 related to 2 to the first power? It's greater than. All right, if it's greater than, then that's the form of our equation. So the form of our equation is big theta of n to the log base b of a. So n to the log base 2 of 3. So there's our equation. Now, I've got a hidden slide here that's got our, whoops, come on, there we go. So we've got that stuff, I've got it all mapped up here. Now, I put an, whoops, I didn't modify this slide. Professor Darden modified this slide on me, and he left one thing off. That should say equals. That should say approximately equal to. So we've got big theta of n to the log base 2 of 3. That's approximately n to the 1.58 power. It gives us an idea. It's not exactly equivalent to that decimal because it's not a terminating decimal. So it's approximately equal to n to the 1.58 power. So we know it's somewhere between linear, it's bigger than linear, it's not as big as quadratic, so we've got a handle on where it is. So that gives us an idea. Now you might say, hey, this is a really odd one, like there's divide by 2 and go into 3 of them. We're actually going to come back and see this one later today in a real problem. Okay, so that was one example. Let's do another one. So here's a new equation. Again, we assume we've got a base case that's constant work. So for this one, take a minute, figure out the a, b, and c for this equation, figure out how a relates to b to the c power, what form of the master theorem we have, which are the cases, and what the final form of our equation is. So take a minute to work on this one. Okay, so for this one, we've got A is what's out front here, is 2. B is what we divide by, is 4. And then C is going to be our polynomial. What is the order of this polynomial? Well, that's n, so square root of n is n to the 1/2 power. So that's our C. All right, so we've got our a, b, and c. We've got to figure out how is a related to b to the c power. So how is 2 related to 4 to the 1/2? 2 is equal to 2. All right, that tells us we're in the second case here. So we've got to have big theta of n to the c power, so that's n to the 1/2 power, times log of n. Now we could rewrite that as big theta of square root of n log of n. Now that is kind of an unusual one, to get a square root in the polynomial part and then we end up with the square root in the final equation. So we've got all that worked out there, so that gives us the final form of the equation. Now we've got another example. Okay, so we've got a new equation. We assume there's a base case that's constant. Figure out A, B, and C for this one. figure out which condition it is, and what's the form of our final equation. And then after you finish this one, we're going to go back and look at what happened with each of these cases and what it meant. And when we're doing these, you can feel free to type into the chat as you start figuring out A, B, and C. That's sometimes how I judge that I've waited long enough and given you enough time. Okay, so let's look at this one. So we've got A is out front here. Well, if there's nothing out front, then A must be 1, because we didn't multiply t times anything, so it's got to be 1. Then B is in the bottom there, so B is equal to 2. And C is the order of this polynomial. This is a n squared polynomial, so C is equal to 2. So we want to know, how is A related to B to the C power? Okay, so we've got 1, 2 squared, so 1 is less than 4. So that tells us we're in the third case. Not surprising. We did example 1 was the first case, example 2 was the second case, example 3 is the third case. So that tells us that we are of the form big theta of n to the c power is n squared. So that's the final form of our equation. Now, like I said, let's take a look back at each of these and solve what happened. See what happened. So let's do the most recent one first. So in this one, we got big theta of n squared. Well, big theta of n squared was the polynomial portion that wasn't recursive. What that's telling us is that in the third case, the non-recursive work was the bulk of the work. So right here, this amount of work there, that was the bulk of the work. That dominated our amount of work. The equation was mostly the part that wasn't recursive for our complexity. Now let's go back to case 1 or example 1. So in example 1, we found we were of the form of a logarithm, n to a logarithmic power. So we're n to a logarithmic power. What this is saying is we ended up here, a greater than b to the c. What this is telling us is that the bulk of the work was recursive. So in case 1, the bulk of the work is in the recursion. It's not in the non-recursive portion. It's not in the f of n, it's in the recursion. So if case 3 is when the non-recursive does the most work, and case 1 is when the recursive does the most work, then case 2 is when they both contribute to the final amount of work. Now granted, they always both contribute to the amount of work, but in case 3, the polynomial is the dominant amount of work. In case 1, the recursion is the dominant amount of work. Here, they're both contributing about equally to the total amount of work done. Now, one thing else about the second form of the master theorem here, notice we have, in the first one, we have n to the log base b of a, and in the second one, we just say log of n. We don't have a base at all. The base is not clear from the master theorem. We might be able to get a better handle on the base looking at the very specific problem that we've solved with the master theorem. But remember what we did when we did the pool balls. Remember how we showed that log base 2 of n was equivalent to log base 3 of n. Asymptotically, all log bases are equivalent. So in terms of big O and big theta, all log bases are equivalent. So the log base in case 2 doesn't really matter. It's n to the c times log of n, and the base doesn't matter. Now, like I said, we might in a specific problem be able to get a better handle on the base, but you're never going to have to do it for the labs or for the exams. If you do solve the master theorem and our answer says something like log base 2, don't worry about it. We're not asking you to determine the base. It's just that maybe we gave you a multiple choice of, square root of n log base. If we said square root of n log base 2 of n was one of the answers to pick from, you'd pick this one because you know it's of this form and all log bases are equivalent. So sometimes we'll do a little bit more work to know that it is log n, but we don't expect you to do that work. Okay, so that got through our 3 examples of using the master theorem. So when can't we use the master theorem? So we can't use the master theorem if n is not monotonically increasing. We can't do it if f of n is not a polynomial. So if f of n is an exponential amount of work, the master theorem falls apart. If we can't express b as a constant, so if we can't say, t of n divided by some number, then we can't do it. There is a special fourth condition for some of the cases of f of n being not polynomial, and this is coming up in another slide or two. So also the master theorem doesn't apply when we've got a subtraction. It only applies when we've got a division. So the master theorem doesn't apply if it's not in this form. Now, that fourth condition that I mentioned. So, if f of n is of the form, is an element of, so if the complexity class of f of n is big theta of n to the log base b of a times the log of n, base doesn't matter, log of n to some power k. So this right here, log k of n, is the same as saying log of n to the kth power. It's just easier to edit it this way in our formula. So that part is saying, hey, we've got log of n, I don't care what the base is, but after we got the log of n, we took it to some power. Well, then what it says is that then t of n is of the form big theta n to the log base b of a. We take the same log of n we had, and we increase the power. So this is one that I would say we might use this for the lab, but we won't expect you to do this one on the exam. And it says there's no need to memorize it or write it down. When I say write it down, what I'm talking about is that if this was a normal semester, you would get a cheat sheet to use on the exam. Now, when we're doing an online exam, you're allowed to use anything we gave you. But a cheat sheet is still a good idea to put the things that you know that you're going to need on the exam. So if you thought, hey, I should have that master theorem handy for the exam, great idea. Much easier than saying, oh, that was lecture, let's look down the schedule topics. That was lecture 5. Okay, let's go find the lecture 5 PDF and page down until I get to the master theorem. Too much time. So working on a cheat sheet now for your midterm is a great idea. Figuring out what's on it, starting to write it out by hand. Again, remember, writing it by hand makes good long-term memory. Or you could even say, hey, I'm going to make a digital cheat sheet of what has to go on it, but a couple days before the exam, I'm going to take my digital cheat sheet and rewrite it by hand, paper and pencil, because I'll remember it better. And then also, another great thing about having it on a sheet of paper is you can be viewing the exam on your computer, and your PDF of your exam, maybe like, or not PDF, sorry, the website of the exam. You can have like a PDF of a certain lecture that you had to look something up, and you got your cheat sheet on paper in front of you, easier to refer to than having it digitally. So you can have more things visible. Okay, so here's an example of the fourth condition in use. So I've got t of n equals 2t of n over 2 plus n log n. So my f of n, clearly not polynomial, but does it fit the fourth case? Okay, well, a is equal to 2, so that's a is right here, b is right there, so I've got a and b. And I've got to know, is big theta, remember down here at the bottom, is f of n big theta of n to the log base b of a power? So if we had a different a and b here, it would have to look different. So we've got n to the log base b of a power. Well, the log base 2 of 2 is 1. Okay, so log base b of a is 1. So we've got n log n. So we do have log n in the form with k equal to 1. So f of n is in this form, n to the log base b of a. So the log base b of a, so log base 2 of 2 is equal to 1. So we've got n, whoops, that's terrible looking n. We've got the form f of n is an element of big theta of n to the first power log of n, also to the first power, that's our k. This one over here is just the log base b of a. It has nothing to do with k. This is our k, log of n to the first power. So that tells us that our final form is big theta of n to the log base b of a, n to the first power, log of n squared. So we could also write this big theta, so t of n is an element of big theta of n log n, and the log term is squared. So that's equivalent form there. So that's an example of applying the fourth condition. Okay, here's a bonus problem to think about. You have a friend who's taking 280. They haven't taken 281 yet. And your friend says, aha, we've discovered binary search, and because that splitting things in half is so powerful, I have found a new way to find the maximum element of an unsorted array. So my new way is I look at each half separately. I find the maximum in the first half, I find the maximum in the second half, and then I take the larger of the two. And then because I'm dividing it in two every time, it's got to be better than linear searching. So they claim that, and you're having trouble convincing them of it. So what we can do is we can use the master theorem to prove it. Okay, so what's our t of n? T of n is equal to, okay, well we got to have something times t of n over something plus some non-recursive amount of work. So let's do the non-recursive amount of work. So the non-recursive amount of work is pretty easy. We figure out where the middle is. After we make the recursive calls, we figure out, hey, I got this recursive call said 12, this recursive call said 17, the bigger of the two is 17. So that's just a constant amount of work there. We divide it in half, but we have to make recursive calls into both halves. So now we've got a is equal to 2, b is equal to 2, c is equal to, this is of the form, this is our f of n, is an element of big theta of n to the c power. What is c here? C is equal to 0. A constant amount of non-recursive work is a polynomial of order 0. So we've got 2. How is 2 related to the 0 power? So 2 is greater than 1. So now you can go back to the page with the master theorem, solve this, and what you'll find is we get big theta of n. So it's no different than doing a linear search for the biggest element. Makes sense. If I've got n elements in an array that are not in any known order, I have to look at all of them before I'm sure I've got the biggest one. Okay, we've got a job interview question here that we're going to look at a couple different ways to solve it. So you go into a job interview and they tell you, we've got a table. It says n times m. So n times m, normally when we say this, this would be the number of rows and times the number of columns. So we've got the number of rows, the number of columns, and it says it's sorted along the rows and columns. So, and when we have subscripts like sub I, sub j, what this means is table, sub row, sub column. So in a double subscript, that's the meaning of the two subscripts. Okay, so when we say table sub I sub j is less than or equal to table sub I sub j plus 1. So everything is less than or equal to the thing to the right of it. So everybody is less than or equal to the value to their right, and everybody is less than or equal to the thing below them. So as we go across a row from, I'll draw it your way, I think it's reversed properly. So as we go from left to right through a row, values never get smaller. They always stay the same or go up. And when we go down a column, as we go down a column, values never get smaller. They can stay the same or they increase as we go down each column. So their question is, how do you efficiently search for a value? All right, well, we can do a linear search of every row. That's n times m. We could do a linear search of every column, still m times m. We could do a binary search of every row or a binary search of every column. So if we do a binary search of every row, we get n log m. If we do a binary search on every column, we would get m log n. So if we do a binary search of every column, we get m log n. And I'm claiming that's still too slow. We can do better than that. Okay, so let's look at a couple different ways to approach this. And we're going to get some, we're going to look at the ways, then we're going to get some equations, and then we're going to show you the solved form of them. Okay, first idea is, let's simplify the problem a little bit. Let's get rid of those two variables, n times m. Let's assume that it's n times n. Let's assume it's square, because even a rectangle can be put inside of a square. So a rectangle is no bigger than the square that would enclose it, and sometimes it's the same size. All right, so we're going to assume it's always, we've only got one variable to describe how big is one side. Okay, so our idea here is we're going to split the region into 4 quadrants, and we're going to eliminate one of them. All right, so let's say, for example, I was searching for the value 13. Now, when I find what I'm going to do is I'm going to look at basically the middle element. I'm going to say, hey, how does that compare to 13? Oh, that's smaller than 13. That means 13 can't be anywhere here. Now, it could be below me. In fact, it is. It could be to the right of me. Like if this 12 was a 13, that would still be sorted along the rows and columns. So it could have been there. And if the values were a little bit different, I could have had like 10, 11, 12, 13 here, and then I would have had to have like another 13 there. And actually, really, let's make this a little bit simpler. Instead of 11, 12, 13, let's just put another 13 here. So this still fits all the conditions, but the 13 could have been in any one of the other 3 regions. So I eliminated one region. I've got to still do the other 3. Okay, so let me get rid of the markings on there. Okay, so if I'm going to split it into 3 regions, and then I'm going to split it into 4 regions and recurse into 3 of them, here's my equation. Now the thing we have to remember is n is not the number of values. N is the size of one side. N is the size of one side. So here, n is not 25, n is 5. So if n is 5, Then when I split it into 4 regions, I make each region n goes down by 2. So n goes down by 2, but I have to make 3 recursive calls to the upper right, lower left, and lower right. So I've got to make 3 recursive calls, but n went down by 2 in this case. All right, so that's one way we could do it. That would work. And we'll look at solving this in a minute. Okay, another idea. Let's split it into 4 quadrants, but I'm going to split it and I'm going to scan the middle column to find, what I'm trying to find is where the value should be, if it was in there. Now, I could get lucky. If I was saying, hey, where is 14? I could get lucky and it's in the middle column and I find it there. Now, we don't have to split it by columns. We could also split it the middle row. Now, we could also split it on diagonals, but that gets really problematical because then we got to do triangles instead of rectangles or squares. So we could split it across a diagonal, but that's not going to work very well. So we're going to do the example. We're going to show splitting it down the middle column, but we could also have split it across the middle row. So we're going to scan that middle column, and we're going to find where the value should be. And the claim is that that's going to allow us to eliminate 2 quadrants. So I'm searching for, let's say I'm searching for 13 again. I'm searching for 13, I scan the middle column, and I see that 13 should be right here, and it's not. If I was searching for 14, I would say, where should 14 be? Well, 14 should be here. I found it, I'm done, I'm lucky. But if I don't get lucky, I want to find out where should 13 be. So 13 should be there, and it's not. Now, what we can do from here is look at the values directly above and directly below where it should be. So we look at the values directly above and directly below where 13 should be, and I see 9 and 14. Now, there's a 9 above me. 9 above me is smaller than 13, and that tells me 13 can't be, I already know it's not in the middle column, I now know 13 can't be here. Because everything above me is smaller than 13, which means everything to the left of 9 has to be less than or equal to 9. So it can't be there. I see a 14 below me. That 14 below me says, hey, 13's not there, but everything below 14 is bigger and everything to the right of 14 is bigger. That means 13 can't be there. So now I've eliminated 2 regions instead of 1 region. And I had to scan the middle column, and when I find out where it should be, I look at the values above and below it. Now, what's my recurrence relationship for this? So here's one possible recurrence relation. So I've got my 2 regions that I have to recurse into. That's this one and this one. The beige and brown. Oh, wow, I don't know those colors. You can play along with me. Bottom left, I'm going to call beige. Upper right, I'm going to call brown. I could be wrong. Anyway, I've got to recurse into both of those. I did split n over 2 because I went from things of size 5 times 5 to one of size 2 times 2, one of size 2 times 3, which is limited by 3 by 3. So I've got a square of 2 by 2, a square that's smaller than 3 by 3. I've cut n in half, and I had to scan that middle column. I scanned that middle column with a linear amount of work, which means I did a linear search of that middle column. Now I could write a different equation. How could I improve that? What if instead of doing a linear search of the middle column, how about if I did a binary search of the middle column? So if I do a binary search of the middle column, my portion outside the recursion changes. The recursive still stays the same, but my amount of work outside of recursion is now log n work instead of linear work. Okay, so that's my different possible equations for this one. So that was, we said here, binary partition, linear search of the middle column, improved binary partition is a binary search of the middle column. So that when we say improved binary partition, we mean split it into 4 regions, eliminate 2, and do a binary search of that middle column. Okay, now some of these can be solved with the master theorem, some not. So the first one, yes, definitely, t of n, 3t of n over 2 plus c, that's our n to the log base 2 of 3, which is approximately n to the 1.58 power. I told you earlier we'd actually see one like that today. The binary partitioning is 2t of n over 2 plus cn. So we plug that one into the master theorem, we get n log n. The improved binary partitioning, so we've got 2t of n over 2 plus c log n. Now this one doesn't quite fit the master theorem. It doesn't fit the first 3 conditions. It doesn't fit the 4th condition. This one actually, you can't master theorem the 3rd one. This one you got to solve by hand. So we solved this one for you. So this one we get big theta of n. So if we do the quad partitioning, we get about n to the 1.58. Binary partitioning, meaning we do a linear search of the middle column, we get n log n. If we do a binary search of the middle column, we get big theta of n. So there's our best one so far. We got big theta of n. Now, there is another approach to solving this that doesn't involve dividing it into regions. So that's the 4th one we're going to show here, is called stepwise linear. Stepwise linear is, what it means is we're going to take one step in one direction at each point. So let's look at code here. So it says, I'm going to give this function a square matrix. I'm going to give it m. So m has to be passed in. N, we assume we know. So anyway, in this function, we know m and n. We know the target. That's the value we're searching for. Like, let's say I was searching for the target value 13. And then row and column. See, I've got to get 2 things out of here. I've got to get where is the row and column of 13, if it's in there. And the Boolean that I'm going to return is saying I found it or didn't find it. If the Boolean is true, then these values have been changed and they make sense. If the Boolean returned is false, so if the return value is false, we don't look at the row and column. They don't mean anything. So if the Boolean returned is false, we can't look at the row and column. They do get modified, but we don't look at the values if the function returns false. Okay, so let's look at what the code says here. All right, first if at line 2, we'll come back to that. We'll come back to line 2 in a minute. It says, line 4 says, let's start at row equal 0 and column equal to n minus 1. Aha. Okay, so row 0, column n minus 1. Whoops, that's supposed to be n minus 1, not n vertical bar 1. So n minus 1 is here. So we're starting here. We're saying let's start searching there. Okay, let's go to the while loop. While the row is less than or equal to m minus 1. So remember, we started out at row 0. So this is saying while the row hasn't gone off the bottom and the column hasn't gone off the left, so while we're still within the bounds, we check if what's in that row and column, so we look at that 15, we say, is that 15 less than our target, 13? Okay, so is 15 less than 13? No. So we go to the else. It says if it's greater than, so if it's greater than the target, which it is, we modify the column. So what's happening here is I'm saying, hey, I'm looking for 13. Is that 15 the 13 I'm looking for? No. But if 13 was in here, it cannot be down in that column. I've got to go to a different column. So we go over to here. So now we go back through the loop. While we're still within the bounds of the array, is that the value I'm looking for? So really, we don't ask for equal first. We check for greater than or less than. So we say, is that value less than my target? It is. So that value is less than 13. That means it can't be to the left. I can move down. Okay, let's go back through the loop. Is that the 13 I'm looking for? No, but it's smaller. And because it's smaller than what I'm looking for, I can eliminate that region and move down. Is that the 13 I'm looking for? No, it isn't, but it's too big. If it's too big, 13 can't be below me. Let's move left. Go back through the loop. That's smaller than 13, so it can't be left. We got to go down. That's bigger than the 13, so I can't go down. I got to go left. Now we come back through the loop. Is it less than? No. Is it greater than? No. Else it must be equal. And I return true. And right now, row is equal to 0, 1, 2, 3. So row is equal to 3, columns equal to 1. And we return true to say, I found it. If we ever go off the edge, we would, let's say we were looking for like 22. If we were looking for 22, we would have gone like down to 23, over to 21, down below 21, we're off the edge, we stop, we return false. So we return false here if we never find it, if we go off the edge. Then that very first if, so we left out one part of this, that very first if at line 2, what is line 2 trying to say? So he says, if the target is less than matrix 0, 0. So if that was true, if the target value was less than matrix 0, 0, so matrix 0, 0, let me get rid of all my markings on here. So if that value, if like it's, let's say the target was 0, if it's less than the smallest value, we return false. We say it's just not in there. Or if the value was, let's say, 50, if we compare it to the bottom right, m minus 1, n minus 1, if we look at that one, we say, hey, 50 is bigger than that. It's bigger than the biggest value. It's not in here. So that saves us from doing work when the value can't possibly be in there. The smallest value must be in the upper left. The biggest value must be in the bottom right. Okay. Also, what if, so like I said, let's say we were searching for, let's find something that's not in the table. 6 is in there, 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 is in there, 16, 17 is in there. 18 is the first value I came across that's not in there. So let's see what happens if we look for 18. We'd say, hey, if this target, let's get rid of the markings again. If this target was, let's say, 18, then I would look here. I'd say, well, that's not it. I've got to go down. So I eliminate this. I go down. That's too big. I eliminate that, and I go here. That's not 18, but I eliminate that and go down. That's not 18. I eliminate that and go down. That's not 18. I eliminate that and go down. That's not 18. Oh, I eliminate everything below me which doesn't exist. I go, oh wait, oh shoot. 18 is, I didn't notice 18's in there. 18's in there, 19's in there. Okay, I goofed. What about 20? It looks like 20 is not in there. Okay, let's change this to a 20. We're actually good up to this point. No, we aren't. We are not. We got to start over. Okay, we'll change colors again. Okay, 20, definitely not in there. Okay, 20. Sorry. And I was like 10 seconds ahead of you guys. And I didn't look up in time. Okay, let's try 20. Okay, so we look for 20 here. That's not it. We eliminate. We move down. That's not 20. Eliminate. Move down. That's not 20. Eliminate and move left. That's not 20. Eliminate and move down. That's not 20. Eliminate, move down. That's not 20. Well, below us it doesn't exist, so we move left. That's not it, move left. That's not it, move left. That's not it, move down. We're off the edge. We failed. Okay, last question. Do we have to start in the upper right? What if I was searching for 20? Again. And so I'm searching for 20, and I start here. Okay, that's not 20. 20 is bigger than that, so I could eliminate everything up there. And I could move right. Okay, this isn't 20, but that stuff's too big. I eliminate that. And I look here. That's not 20, too small, eliminate, go right, eliminate, go right, eliminate, go right, go up, go off to the right, and I'm off the edge. So I could start in the bottom left. I'd have to change the code. I'd have to change line 4. I'd have to change line 5. And I'd have to change 6, 7, 8, and 9. So I'd basically have to modify 4 through 9. So if I modify 4 through 9, I could start in the bottom left. Okay, with few minor changes, I could start in the bottom left. How about, could I start in the upper left? I'm looking for 20. That's not 20. You can eliminate nothing. You can go right or you can go down. I don't know which. That didn't help. What if I start looking for 20 here? Well, that's not 20. Could be above you, could be to the left of you. I don't know. Go both ways. Doesn't help. So this one, we can start in the upper right. We could recode it to start in the bottom left. Either of those will work, but we can't start with the smallest value or the biggest value because we don't learn anything. We might learn that it's not in there. I'm searching for 50. It's not in there. Done. But if it is in there, I don't know whether to go left or go up, or whether to go right or go down. So let's get an idea. Now, we're not going to write a recurrence relationship for this one, but let's get an idea of an upper limit on the complexity. So we could always get lucky. So the way it's written, I could start searching for 15, and I find it, I'm done. I could always get lucky. But if I don't get lucky, I always move down or left. So I always move down, left, down, etc. How many times can I move before I go off the edge somewhere? Approximately 2n. So at most, I can move around 2n times. It might be like 2n minus 1 or 2n minus 2, something like that. I think it's 2n minus 1 at a guess. I think it's 2n minus 1 is the most it can possibly be, which is big O of n. Well, it's the worst. So the worst possible is big theta of n. Or we could just say this thing is big O of n. So the worst is big theta of n. It is also big O of n in general, because you could get lucky and find it at 1, or it could get there. It could be, well, it would actually be n plus m minus 1, I think. I was using n here to be only 1. But yeah, it's either 2n minus 1 or n plus m minus 1. If we treat it as it's always the same size, it's 2n minus 1 or n plus m minus 1. So it's basically, it's linear. Now, oh, wait, come on. Oh, yes, there was an example there of finding something. Okay, so here's actually implementing all of these. Links to a website that's got them all implemented. And what the person did was they filled this big array of size 100 by 100 with random values and searched 1,000,000 times for different values. And so, binary search, this is saying, let's binary search every row. So that's binary search every row. Let's binary search every diagonal is worse. Stepwise linear is the one we just did, is pretty good. The quad partitioning, remember the first one where we were eliminating one of the 4 regions, is worse than that. The binary partitioning, so if we do a linear search of the middle column, is worse than the stepwise linear. And that one's pretty good. It's n log n, and log n is pretty small. So that one's not too bad, although the improved binary, which is a binary search of the middle column, is the best one. So this one is at worst big O of n. This one is at worst big O of n, but they're both big O of n. The bottom one is a little bit faster. better constants, better use of the cache, etc. And I'm over by 10 minutes. I didn't realize it was so late. Okay, we got to finish up here. All right, I'll see people in office hours.